Okay. All right, welcome everyone. I'm Paul Ferraro from Johns Hopkins University, United States, and I'm co-hosting today's seminar with my co-host Joanna Eklund from the University of Helsinki and Sebastian Costa-Doat from Conservation International. If you haven't been in the seminar before, we ran it all last year, and we're going to continue running it through this year because we had such a great response from you all. We'll be fleshing out the rest of the schedule soon. You'll be getting updates if you've registered via email. So if you haven't been here before, I just want to cover some of the basics of how we run these seminar series. We start with the speaker, followed by a moderated Q&A session. And for the moderated Q&A session, you can post questions in the chat, and we encourage you to do so early and often. That makes it easier for us to go into the Q&A with some questions already ready to go. This is a very safe place for you to put questions in there, so don't feel hesitant or that you might be embarrassed. We're all learning stuff from the speakers. We all have many things to learn, so feel free to put in questions into that. And we get often a lot of questions. We might not be able to answer them all, but we try to do the best we can. If you find it helpful, you can activate the live transcription function in Zoom. It's under More in the menu ribbon, and you just choose live transcript. The seminar will be recorded if you have to leave early, or if you know someone who would be interested in seeing this seminar, and you can find them on the Society for Conservation Biology's Vimeo channel. And we will send out an email to all registrants once that video is ready. If you want to engage with us on social media, please use the hashtag Tuesdays with Team Counterfactual and tag @IDoImpact, which is the Twitter handle for SCB's Impact Evaluation Working Group. It's a provisional group, but we're trying to turn it into a permanent working group. So please join if you're interested in this topic. You can find out more at those websites, and we'll also put them in the chat box for people to follow up with. You can follow us on Twitter at @IDoImpact, and you can sign up for the email list where you'll get information on presentations, sessions at different conferences, and other relevant materials. It's not a heavy amount of email, so I encourage you to sign up for that to stay involved. Today, we have the pleasure of hosting Professor Jennifer Alix-Garcia from Oregon State University in the United States. She's done some of the most rigorous and careful impact evaluations for payments for environmental services, as well as a range of other environmental and development interventions. And she has the first, or one of the first, careful impact evaluations of the environmental effects of anti-poverty programs. It's a paper that, in my opinion, is one of the most underread and undercited papers in the conservation literature. It's called The Ecological Footprint of Poverty Alleviation. If you haven't seen it, I encourage you to check it out. But today she's going to be talking about an underappreciated issue in impact evaluation, as if we didn't have enough issues to address already. She's going to talk about another one that I think is important, not just in the context she's going to be talking about today, but all contexts in which we are measuring these conservation outcomes imperfectly. This is going to be an issue for all of us. So I'm going to turn it over to Dr. Alix-Garcia. You can take it away.
Thank you so much, Paul. That made me blush a little bit. So I'm going to recover and share my screen here. Let's see. How's that looking? Thumbs up on that, Joanna?
Looks great.
Okay, thank you. All right, so thank you for that nice introduction and for inviting me to present. I'm really excited to be talking with this very diverse crowd who bring expertise from so many different areas. I think the conversation afterwards will be pretty fascinating. I am going to talk about measurement error today, and I'm thrilled that so many people have shown up to listen to this, but I also want to open with a few reflections on the challenges and opportunities that I see for bringing together remote sensing data with impact analysis. I'll talk both about things I've seen as an editor and reviewer who looks at a lot of papers that pull these two things together, and also as a researcher who tries to do this stuff and has made all of these mistakes. So do as I say, not as I do, I guess is one of the messages here. So I know I'm preaching to the choir with this first slide, but I think it's worth emphasizing what a bonanza remotely sensed data is for those of us who care about environmental and resource management issues. We now have global information on all kinds of outcomes that are really cool, land use, measurements of previously unobserved resource extraction like illegal mining and illegal fishing, important determinants of economic activity like rainfall, temperature, and topography. And all of this stuff is just amazing. And I'm so grateful that other people have created it. In contrast with a lot of the data that people like me use, for example, household survey or administrative data, remotely sensed measures have huge samples, like the census of the world in many cases. So you don't have to worry about things like sampling or non-response bias. You don't have to pay enumerators to travel to remote and sometimes dangerous settings. And you don't have to worry about or mostly you don't have to worry about people trying to make the data look like something that they think you want to see. And furthermore, the resolution can be unbelievable. So that in this slide on the left, this figure shows Facebook's preliminary estimations of population in the Democratic Republic of Congo at a 30-meter resolution, which isn't even as low as it goes, as everybody knows, but this is a notoriously difficult place to get information. So all of this stuff is fantastic. And I want to take a few minutes to walk through some of the ways in which it might not be fantastic, landing on measurement error as the last one, and then I'll lead into the recent paper that I've been working on. So for people who create this kind of data, I'm imagining that there are some of you in the crowd today. This slide is for you. It's important to realize that people like me are taking this data and using it in ways that it might not have been created for. So most policy analysts want to have measures from before and after a policy event in places that are affected by a program of interest and places that are unaffected by this policy. So you've probably, I haven't watched all of the videos from this series, you've probably seen a figure like this before. The outcome is on the y-axis and time is on the x-axis, and you measure impact of a program by comparing the before and after between affected and unaffected areas. You get extra credit if you have used randomization to create your treatment and control groups, but there are quasi-experimental ways to do that too. But the point from the perspective of the person who's creating the data for this, who might not be used to frameworks like this, is that we need these kinds of data to have particular characteristics. For example, I know that it sometimes happens that images for multiple time periods are mosaic together, and the person analyzing the data might not understand this. But when you take multiple time periods, you might be pulling from this period and not attributing those time differences. Our methods for impact analysis also require that the measures we use are consistent over time. So it's always great to improve the algorithms that are used to generate data, but when you're constantly changing the way you measure an outcome, it makes it difficult to use it to measure the trajectory of change over time. In order to best use information in a remotely sensed measure, analysts need to understand where the classifications perform well and where they don't, and why this is. So this helps us understand how measurement error might enter into the estimations that we're doing. So I'm going to circle back to this in a couple minutes, but I first want to mention 4 other challenges that face the users of this data that would benefit from more open discussion. So the first of these is simply to understand that remote sensing data results from an entire process, and it's not simply spit out from a sensor ready to use. And furthermore, the measures that we end up using aren't always what we want them to be. So for example, NDVI, which is a commonly created measure of greenness, is not equivalent to deforestation, and nighttime lights are just a measure of light. So understanding how to translate these outcomes into the actual phenomena that we wish to observe often requires some deep thinking and discussion with the people who created this information. Spatial data can be aggregated and scaled in many ways, and actually has to be in order to be analyzed, since we sometimes need to connect it with other information like plot level boundaries, household survey, or census data in order to analyze it. So this leads to a well-known problem in geography where the same data can yield different results when aggregated in different ways. This problem is sometimes called the modifiable aerial unit problem, and a common example of this is gerrymandering, big topic of discussion with the creation of new districts in the United States after the 2020 census. So on the right-hand side of this slide, you can see a more geographical example of this issue. The first map shows the baseline DEM data at a 30-meter resolution. The second aggregates this up to 15 by 15 kilometer grid cells. And the third aggregates up to a very common unit of analysis for people like me, which is political boundaries, and these themselves are endogenously determined usually by population. A related issue is the fact that the units that you're analyzing might vary a lot in size. So for example, if you're analyzing properties with varying areas, which are subject to the same policy, it's entirely possible that you'll get a different answer to the question of, for example, if a policy has affected agricultural yields or deforestation or whatever outcome is of interest to you, if you weight the data in such a way that every hectare is of equal interest versus if you don't, in which case you're calculating the effect for the average property. So both of these outcomes are interesting, but they mean different things. A misconception that I often see when I review papers is driven by the fact that you can make very large samples when you have access to very small pixels. And that allows you to break up the space into ever smaller units. However, it's important to remember that just because you have a lot of observations doesn't mean that they are independent of each other. In fact, it's very likely that they're not independent of each other. So you can see in this map how these colored properties, the things that are not green, which are properties that enrolled in a Payments for Ecosystem Services program, are clustered together across space. And they also, in the bottom graph, you can see how they cluster across time. So these are shaded by time, with warmer colors being earlier and cooler colors being later. Both these levels of visualization show that these applications are neither independent of space nor time, and these correlations need to be taken into account when you actually put together the information to analyze a program like this. Finally, and this is related to my initial plea for understanding data accuracy over space, we often think that variables are normally distributed when we analyze them using econometrics, and that their mismeasurement is also random and normally distributed. We also often believe that error in the outcome variable is not a big problem. However, for a number of reasons, these things may not be true for satellite-based measures, and therefore they might suffer from non-classical measurement error. So non-classical measurement error is a terrible thing. It's also a problem that we've known existed in lots of different kinds of data for a very long time. So nothing that I am going to say about how to deal with measurement error in satellite data is very revolutionary. This all draws upon existing literature from people who've analyzed mismeasurement in different kinds of variables of all different types. I think the important thing is that I think there's a tendency for analysts to believe that everybody else's data is measured better than their data. And when you look at data that you download from satellite-based measures, it always seems like it's perfect, you know, because A, you don't know exactly how it was made, and B, it looks so complete. But in fact, it's just data like all the other data, and there are ways in which the measurement error might enter, and I'm going to talk about this in the next couple slides. So I've just wrapped up a paper that examines measurement error, focusing specifically on outcome variables. So this paper is co-authored with Dan Millamette, who works at Southern Methodist University and from whom I learned a ton working on this paper. He working on measurement error in different sorts of settings. So this paper is forthcoming in the Journal of the Association of Environmental and Resource Economists. And so if you want the details of it, it's kind of technical, but if you like that sort of thing with many tables and equations, you can look at the Jerry website for that. So what this paper does broadly is first discusses how measurement error might enter into remotely sensed data. Second, it uses an example of two different measures of forest cover in Mexico to highlight where measurements might differ. In the second part of the paper, we propose an estimation technique that you can use when you have a binary dependent variable that has misclassification. And we conduct a Monte Carlo simulation to show that the estimator works well. So specifying a data generating process that looks like something that we see in data sets that we've used before. And then we also apply this estimator to an application of a conservation program in Mexico. So where does the error come from? Well, this discussion that I'm about to show you presents potential sources of error from optical remote sensing data. I don't know very much about radar or LiDAR at the moment, and I think some of these ideas are generalizable, but I'm a little uncertain, so people can correct me in the discussion part of this forum. But error in optical remote sensing can come from one of three places. So first, there can be technical limitations that make it that the image you're trying to collect isn't perfect for your analysis. Could be you're measuring something at the wrong scale. So you have pixels of 1 kilometer, but you're interested in behaviors that take place within a plot of half a hectare. Some satellites develop problems as they age or right away, as is the case of Landsat 7, which is a satellite that provides a lot of data for land use models and suffers from what is known as the scan line error, which means that many images have stripes of blank data throughout the image. There can also be atmospheric interruptions like clouds that mean that the satellite can't see the ground. There can further be topographic challenges where when a satellite is passing over the Earth at a particular moment, there are shadows that are cast by mountains. And the second source of error comes from trying to deal with this issue. So what creators of this data often do is they mask certain parts where the data is poor, and they either interpolate or replace that data with alternative data sources, sometimes from different time periods, sometimes from sensors of different resolution. These substitutions are unknown to the end-line analyst and create measurement error. Finally, optical sensors only measure reflectancy. So this information has to be translated into stuff that we can use as an outcome. And this translation is done with algorithms of all different types. And we know for those of us who work with algorithms, it's never perfect. There's always some kind of error around it. And the translated data that we get from remote sensors is no different. So at the end of this whole process, you have your data. And off you go with these three potential sources of measurement error in the data, some of which are correlated with topography, which is an important determinant of many of the things we're interested in conservation. To show how this kind of classification problem actually manifests itself, we look at two separate data sets that are trying to measure the same phenomenon for the entire country of Mexico. So the first measurement comes from the government of Mexico, and the second comes from the Hansen lab at the University of Maryland. So both of these measures use the same kind of imagery as an input, and they're measured at approximately the same time. They're different in that the Government of Mexico series needs to be reclassified into the simple categories of forest and non-forest because it has more complex classification scheme. And there are other small differences between these two data sets, but the main point is that if you were trying to analyze forest cover across Mexico, you could reasonably choose either of these two sources of information. We aggregate the data up to 5 by 5 kilometer grid cells across the entire country, and then we attach other information like slope and elevation, forest type to these grid cells. And we count the number of available images that might have been used to create the data by just going into the archives that are available. When we classify each grid cell as either having some forest or not, we find that the two data sets are in agreement about 78% of the time. That means that they disagree the rest of the time. We don't have a strong feeling about whether one measures forest better than the other. And for our purposes, it doesn't really matter. We're not trying to make that sort of assessment. We also observe that one of the metrics measures almost twice as much area of forest on average per cell. So there's disagreement on both the existence and the quantity of forest within our analysis units. We further show in the paper that the degree of disagreement between these two classifications is systematically related to geography, cloud-free image availability, and the interaction between the two. So the misclassification is driven by, just to repeat what I said before, some of the characteristics that probably drive land use change behavior, and others which are simply technically related, like the availability of images. So I'm going to return to this when I talk about our application. So because we think that this measurement error is potentially problematic, we look around for ways to help. This situation has been dealt with in a number of papers that look at independent variables, so the right-hand side variables, not the outcome variables. So because of this, we focus on the case for the dependent variable. The other reason why we focus on the dependent variable is because I think that's important. And it has been my experience in talking with people who operate these kinds of programs that they believe that the outcomes are often very mismeasured, and they worry that the mismeasurement of these variables ends up misrepresenting how effective the programs actually are. So the focus of our analysis is driven both by the fact that the right-hand side problem has had many people address it, but also by the fact that policymakers have expressed concern about mismeasuring the main outcomes of what they're doing. We focus on the binary case, which means a 0-1 indicator of either forest, no forest, or deforestation, no deforestation. This is useful because it frequently occurs in these kinds of analyses, and also at its root level, even if you aggregate up the data, most pixels are classified as being in a category or not. Now, there are some layers which have probabilities associated with those, but much of the publicly available data is classified in a binary way. The other nice thing about this focus is that we actually have a solution. So the measurement error in the binary outcome in this situation is non-classical, both because it is what we call a limited dependent variable. So the structure of the variable itself creates an endogeneity problem, which generates bias in the estimated coefficients in your impact analysis, but also because the error might be correlated with variables we're interested in, like geography. So there are two reasons why the measurement error is non-classical: the form of the variable and the correlation of the measurement error with environmental factors. Aggregation does not eliminate this problem. We show that in the paper if you're interested in that. exercise, and randomization does not eliminate this problem either. So the solution that we propose involves directly estimating the probability of measurement error. We're able to do this because we think that measurement error depends upon observable things that are not necessarily in the main equation for estimating the forest or deforestation outcome. So we think the measurement error depends upon cloud-free imagery and its interaction with geography. We propose a modified maximum likelihood estimation that estimates this misclassification probability simultaneously with the outcome. And we can also modify this to take into account the fact that deforestation can be a rare outcome. So a rare outcome means that it occurs pretty infrequently. And we often see that with deforestation rates can be quite low, which means that your probability of observing deforestation, if you look at a random sample, is pretty small. We provide code for all the estimators that we use. And if you're interested in that, you can either download it from Dan's or my website or from the Jerry repository on Dataverse. We conduct a Monte Carlo simulation to test how well these estimators work. So a Monte Carlo simulation allows us to control the data generating process and look at how our estimators perform relative to what we think might be the best case scenario. So you don't have to digest this figure on the right. It's there more to provide visual variety, but it shows the root mean squared error of the estimated treatment effect in the model that is described in the legend. So all these different models relative to the best model. So the main point of this is that if you look across the x-axis, these are different kinds of data generating possibilities. So more error, more skewed data, less skewed data, but all of these points that show you the how well the estimator performs, when they're higher than 0, or when they're higher than 1, actually, it means that they are much worse than the optimal outcome. So some of these have a root mean squared error 15 times higher than what we would hope to have. The models that don't adjust for measurement error can be immensely inconsistent. And some of the corrections that we sometimes do, like adding covariates that we think might be correlated to mismeasurement directly into the model, it doesn't help the performance of a basic regression model. In fact, it makes it worse. The Monte Carlo also demonstrates that taking into account the structure of the data in terms of rareness of deforestation outcomes can be very important. You get much better, less biased measures of the treatment effect when you take into account the skewness. And finally, measurement error need not lead to estimates that are attenuated or underestimates of impact. The bias can go in either direction. This might go against what you think you remember from your elementary statistics or econometrics classes, where noise in the outcome variable leads to attenuation. The reason why this happens in this case is because this isn't classical noise. This is noise which is very correlated with the error term and therefore can produce a bias that goes in either direction. This is problematic for impact analysis because we often like to say, oh, we had problems, but we underestimated the result, and the fact that we see an effect is great. But in the presence of this kind of measurement error, you're unable to say that. The last section of our paper applies our estimators to some real data from a forest conservation program in Mexico, where the main goal is to measure the impact of the program on deforestation. So the sample here includes all land that ever applied to the program, even if it was rejected. These are 5-year contracts where people voluntarily try to enroll their land. And because there's not a large enough budget to fund everybody who would like to enroll their land, there are rejected parcels. The unit that we analyze is a polygon with a unique boundary. So we're aggregating up a little bit this data in this setting. And the outcome that we look at is deforestation. So we have annual measures from the Hansen product, and we create a binary outcome where when we look across all of our polygons, about 17% of them are observed to be deforested using this data. We use a variety of different approaches in terms of covariates, but the main ones are to use either municipality or polygon fixed effects. In the event where we're using municipality fixed effects, which controls for all time invariant municipal characteristics, we also include geographic covariates like elevation and slope and biome. For correlates of measurement error, we have the number of cloud-free images and its interaction with slope and elevation. So these are the things that allow us to predict the presence of measurement error in this data. So these bars represent the interquartile range of observation-specific marginal effects that are the treatment effect of this program. So if you look at the x-axis, you'll notice they're all negative. So overall, no matter what estimator we use, we observe that enrollment in the program decreases deforestation. These bars at the top that have the MC next to them and this one, these are the bars that correct for the misclassification error. These bars at the bottom are the ones that don't. These are standard models that one might use in impact analysis, some including variables known to be correlated with measurement error and some not. A few things to conclude by looking at this are that the estimated effects are larger in the MC, the misclassification corrected estimators, meaning that in this particular case, using the standard models produces attenuated outcomes. So you underestimate the treatment effect. That's not guaranteed. And all of these estimators suggest the presence of misclassification error. So we see that by looking at these graphs. So these show the distribution of false negatives using the different estimators. This is essentially the same information. So this is the probability of misclassification using the 3 different estimators that we use. The most basic model estimates a higher level of misclassification than the estimators that adjust for rare outcomes. So the lesson from this is adjusting for the fact that your outcome is rare might be important in using an approach like this. In the model that fits best, we estimate that the true proportion of units deforested is at about 22%. So this level of misclassification is consistent with other work that shows a high presence of false negatives in tropical countries, looking at comparisons of this particular data set with more detailed assessments of deforestation from those regions. So you have information from Madagascar, Brazil, and Ghana, all of which confirm that with this kind of global product, you can have high rates of misclassification locally. So just to wrap up, I don't want you to feel discouraged. You should feel like, oh, I want to use this kind of data because it's really powerful, and I hope that everybody continues to do so. But I would also encourage people to think hard about how you use these remotely sensed measures. I've tried to highlight some issues that I think would be good to keep in mind here, and we provide our estimators for people who might want to use them. And I think we have made a little advance in thinking about measurement error, but maybe the most important thing is just to know that it's there and to interpret your results in light of the fact that you know that it exists. And I hope that this starts a conversation that can lead to new and exciting evidence about what works best in conservation. Thank you.
Thank you so much, Jennifer. This was a really fascinating talk. And now I just open the floor for questions. So if people in the audience have questions, please post them in the chat and I will try to moderate it from there, forwarding them to Jennifer. But I thought while we are waiting for people to get more active, there's one question. So in your paper, you were using treatment as binary, but there were some people in the audience that say that they are using continuous measures. Do you have any idea how this might affect the results that you found?
So did they treatment or the outcome is binary?
Sorry, outcome, I assume.
Yeah, okay. So we don't yet have a solution for this continuous variable problem. You could, in theory, if you had like an ordinal variable, for example, restoration, no change, and deforestation, something like that. In theory, you could modify this likelihood function to do that. We haven't done that yet. I think that there isn't yet a solution for a truly continuous variable, but I think that is an interesting thing to think about for sure.
Definitely, thanks. And then there was also some questions related to the randomization. So I feel that you were saying that randomization, even if the treatment would be randomized, it wouldn't necessarily help. So why is this the case? Won't the same factors driving the measurement error be uncorrelated with then, if so, the treatment variable? I mean, if the treatment were randomized.
Well, it's not. So when you have measurement error, so there's two reasons why that's the case. So the first is that when the outcome is binary, it means that you can only have error. The average error is negatively correlated with the outcome, because you can only, if you have 0 and 1, you can only have a 0 error or a -1 error. And so that's just mechanical. The other issue is that if the measurement error is correlated with these geographic variables, it's not that if you randomize treatment, you break that correlation within the treatment, but you still, when measurement error affects one variable in a regression, it affects all the variables. You can't like get rid of that dirty correlation, that bad correlation, by just randomizing one of those things.
Right, thanks. And then we'll continue. So there's one person asking, just so I understand your solution requires you to know some correlates of the measurement error, correct? Does this leave a problem if there are sources of correlates of measurement error that are unknown or unobserved, which I guess is a larger problem in general with impact evaluations, but particularly interesting in this case?
Yeah, so it is always a problem when we don't know. That not knowing things is always a problem, and in this case, I think it is equally so, because really you are making an assumption that you kind of know a little bit about the form of both the main outcome and also the measurement error. You want to have some understanding of how those things work. I think formally in the paper from which this estimator is derived, there is an assumption that if you have a continuous variable in the main equation that's not in the probability of measurement error, you can identify this. But I think in practice, it would you might have specification problems if you don't have a good sense of what you should put in both parts of the estimation.
Yeah, that's really interesting. Now continue a little bit about these things in practice. So somebody is saying that really happy to hear that you're still hopeful, despite the fact that this might feel quite discouraging for many of us, having used some of these data sets for many years already. So the question is, with a 78% of agreement in these data sets, that's the two that you were comparing, in practical terms, with your proposed approach, what is the gain for policy advice? So do you, like, to what extent do you think this will actually change the conclusions that starts to build up in terms of whether there needs payment for ecosystem services or protected areas or other policy, conservation policy tools?
Yeah, so I think we don't have a way to bound the size of the bias introduced by measurement error. In the case of our specific application, the bias is not huge and wouldn't change your policy advice, but that's not true in all of the Monte Carlo simulations that we run. In some cases, the bias is very large. That's an interesting thing to explore. So how big would it have to be for you to want to change the policy advice that you give? I'm not sure. I have to think about that. I think I see that question comes from Carlos. So if you had multiple outcomes, one thing that's not clear probably in the presentation that I just gave is that we're using different data sets in the empirical exercise than we are in the comparison, because we actually have two data sets that measure forest, but only one that measures deforestation. So ideally, if you had multiple data sets, it would be nice to be able to run the same estimation using both of those outcomes and make some comparison. And that might give you a better sense of whether or not you get different enough results for that to be worrisome.
Yeah, no, I think this is really interesting, and I guess this relates a little bit to, of course, this would be kind of purely based on your context-specific expertise, but how far do you think these things could be generalizable to other types of land use change data sets or other type of data used as proxies? So, for example, I've been using myself for Madagascar fire incidents, or as you were mentioning, nightlights, or these other type of like also openly available data sets that I think currently there's a lot of interest in conservation for them.
Yeah, I mean, I don't know tons about how that data is created, but I think maybe a generalizable lesson is that talking to the people who make those data sets and actually do the processing of it and asking them, they know where there's error. They know where the error comes in. It's just not always part of the papers that they publish. So sometimes you get accuracy assessments of data that are for the whole data set and not by region or by according to, like for us, things that we might include in our regressions. This kind of information is great to have when you're trying to figure out how to best work with that data. And I would like to emphasize, I don't think I said this maybe loudly enough, all the data we have is measured with error. And if you've ever conducted a household survey or tried to survey people and watched the application of a survey, you're probably acutely aware of that. So this problem with the remote sensing data is the exact same problem that we have when people tell us that, you know, somebody was born in 1980, but they're 10 years old. You know, this is the same. These are like the kind of things that happen when you are collecting data. But it's nice to have these large data sets. So we just have to figure out a compromise where we are doing smart things with it, understanding that it has imperfections.
Yeah, I think definitely I agree, and I think this is really amazing to see such a big amount of people zooming in for this meeting. I think there's a great interest for us to learn to better use these data sources. Well, I will continue with one. So far we've been speaking mostly about kind of errors arising from kind of spatially related things. But there's one which of course might also be related to the temporal dimension or temporal resolution of these type of data sets. Jorge is asking, I have a question about errors in temporally estimating deforestation when using yearly deforestation products such as the Hansen data. There might be uncertainties about the actual year when a given pixel was deforested due to seasonal dynamics of the forest clearing process and the date that the satellite image was acquired. The specific cloud cover in a year that would make the pixel only appear deforested the following, and so on. Do you have any sense of how severe these type of errors could be and ways around this?
Well, this type of error is actually accommodated by our estimator if you're using the binary outcome, because we're using information on the availability of imagery to predict the on an annual basis to predict the misclassification problem. But conceptually, that's a big problem, because when you think back to the that simple framework that I presented at the beginning, where you have before and after enrollment, if you move the window of detection of deforestation around that time of treatment, then that's a significant problem of misattribution.
Excellent, and I see we have so many questions, but at least one that I picked up here is related to measurement error again. So when the measurement error is related to the deforestation behavior, such as, for example, more likely when deforestation occurs in small patches, do you have thoughts on what you would use as a correlate of measurement error?
Yeah, I think you could include the area of, so if you and we actually did this in some of our estimation, you want to use some of those features of the sensor itself, because those really help capture the temporal dynamics. But in some of our estimations, we also included the interaction between that and the parcel size that we were looking at. And that parcel size was important in predicting the scope of the error, because I mean, just mechanically, if you're looking at if you're aggregating over much bigger areas, you're going to get a better approximation of what's happening over that large area. And also in a very small area, probabilistically, you're just less likely to observe anything at all. So these things about unit of analysis size interact with the measurement error, and that's very perceptive, Jorge.
Thanks so much. And actually one rather practical one. So let's imagine that all of us would now like to use your tool to better actually make sure that we are accounting for these things better. And I think one question that might have remained unclear for some of us is that, so you mentioned that we need to jointly estimate the measurement error, but does this mean that we would need to use kind of starting from unclassified pixel level data, or could we just directly apply these to already classified data sets such as Cropscape or Hansen or other existing data sets that are kind of already classified?
Yeah, our approach is to use the already classified data. And I mean, in a way, it's kind of suboptimal, because you're like saying, okay, here's this, we're going to guess where the error was in this data. That's essentially what we're doing. There is a new paper by Rodriguez Sousa that appeared in Review of Economics and Statistics, where they try to fix the error before using the data. So that's a different approach. I can somehow find that information, not at this moment, but I can share that information with people. So ours is an approach where you're doing the correction while you're actually estimating the treatment effect just with the available data.
Okay, well, that's great clarification. So that means that after this, we have no excuses anymore not to actually improve our data sets. But in relation to that, perhaps a little bit of a critical comment. So as you said, the errors can be correlated to other variables that are observable, but those variables themselves are probably also containing errors. So is there any risk that I would actually add more bias to the estimates than actually correcting them? And where would you, if so, kind of draw the line?
Yeah, that's a great question. Dan and I have talked about that, and that is true. What we think for most of the variables that we include in trying to correct the measurement error, they're pretty well measured. Like the number of missing Landsat images is pretty well measured, and we believe that the digital elevation models that we use are as good as they can be. But those two, you know, they are not at the most fine scale, and so that could be problematic. I'm not sure to what degree. We haven't. That would be an interesting simulation to do, to try to figure out when you overlay mismeasured variables into the prediction of the mismeasurement, what happens. I don't even know. I can't speculate. That's a great question.
Yeah, I guess, like, you know, it's like this risk of opening Pandora's box, and then you just get more and more caught up. But anyway, this is great. Finally, I see that there's definitely several calls here for more collaboration with people working on GIS data sets, remote sensing, but actually also wildlife ecology. So to what extent are this approach that you're suggesting different from, for example, different type of existing zero inflated corrections in ecological modeling? Because I feel sometimes there's a divide between kind of approaches coming from, or statistics being used in ecology and econometrics, and basically they are actually doing the same thing. So any comments on this? Or
I don't know. I'm not sure. I can't answer that question.
Yeah.
This is, I mean, usually, so what I find when I talk to people who work in other fields about what we do in economics, I think what we tend to do differently is that we're trying to make estimators that operate within the causal inference framework. So we're thinking about how does this measurement specifically affect the point estimates that we get of an effect of a program. So we're always thinking about the counterfactual, which is something that ecologists, I think it's not as natural for them to think in that kind of framework. So I'm not sure how they deal with the counterfactual question using zero inflated things, like you just said. I don't even know.
Yeah, I guess there's exactly a lot of parallels still to kind of distribution models where you have a lot of zero observations. But hey, I feel I'm almost sorry that we have to stop this discussion. So there's definitely several questions that we haven't had time to address, but I would need to take the last minutes to actually flag next month's upcoming seminar. But please, let's continue this discussion on Twitter, and then of course in all the submitted papers to come based on Jennifer's approach. So yes, before we close for today, I just want to flag that on the 7th of March, so the first Tuesday of March in a month, we will actually have a panel discussion related to counterfactual methods and how they are being used in the voluntary forest carbon market, past, present, and future. The speaker list is currently being finalized, but I think this will be a really topical question, seeing, I don't know how many of you might have seen the Guardian had a big piece about this, and there's been several quite interesting new pieces of research also coming out in this sphere. So we're really looking forward to hear from both people in academia, but then also practitioners and people representing industry or the carbon market companies. But yeah, on my behalf, thank you again to Jennifer for such a brilliant talk. I think this was definitely super interesting and a great way to get back after the holidays. And thanks also to Paul and Seb for helping with hosting this seminar. And if there's nothing more, then looking forward to seeing all of you next month.
Thank
Thanks
you
so
so
much.
much.